All right, let's talk a little bit of schedule here, how things are going. So we're Wednesday, May 6th. Next week is the last week of classes. Class 36, class 40 is the last day. Today I am going to still continue to focus on, well, what I didn't get to last time was gradient systems. I'll talk about that. I'll still talk about the extra reading assignments to some extent with the trapping regions especially, and an application of trapping regions to the van der Waals system, and also something called the Poincare-Bendixson theorem. I'm going to start chapter 6 a little bit today. Try to carve out about 10 to 15 minutes hopefully at the end to start it. You have to take some things on faith and do the reading, but also you can watch the extra optional videos where I go into a little bit more depth than I'll probably have time for here today. In coming days, we'll continue in chapter 6 and then continue reviewing some things in chapter 5 to try to figure out what's a reasonable thing to be able to test you on, with especially with the extra readings on the final exam. So that's something that I'll kind of try to work out as we go here. I'll probably send you some information about some of the problems on the final exam that are not related to the extra readings, but then we still need to figure out what could go on the final exam that is related to the extra readings. And the final exam for us, again, is late in finals week, face-to-face final exam, Friday, May 22nd, 11:30 to 1:45. I cannot change that time, that's set in stone. There are ways you can appeal to have it at a different time. Couple sets. I think if you have 3 finals on one day, you're allowed to appeal to change at that time. But otherwise, we have to leave it on that day. The online people, for those online, you have 2 options on Wednesday the 20th, either 8:45 to 11 or 1 to 3:15. And so eventually you're going to want to let me know. And again, this is just for 2015 classes. In the future, these times could be different. Project again is due Thursday, the week before finals, by 9 o'clock in the morning. And you can ultimately send it to me electronically. Through email would be probably the easiest way to do it. All right, let's start with the thing we didn't quite get to last time. Let's talk about what are called gradient systems. Gradient systems are very similar in some ways to Hamiltonian systems. They're sort of what you might call the dual system. They're related to each other. Any given function that we're used to, nice functions, can generate a Hamiltonian system and a gradient system. It can generate both. And the phase planes are related to each other, actually, in a way we're going to see here. Doesn't mean they have, if you just come up with some arbitrary function, that it's a natural function in some application. But definitely you can create a Hamiltonian system or a gradient system right away. So I've got a function here. Capital G is what I called it. G of xy equals x cubed minus x plus y squared plus x times y. Oops. No, that's right. I think that's right. Yeah, okay. Given this function, we can create a Hamiltonian system. Don't be misled by the fact that I'm calling this function g. It's going to be a Hamiltonian function for this Hamiltonian system I'm about to write down. dx dt is the partial of this function with respect to the second variable. And dy dt, the derivative of the second variable with respect to t, is the opposite of the partial of g with respect to the first variable. What does that simplify to here? Take the derivative of g with respect to the second variable here, y. You're going to get 0 there. You get 2y plus x. Or if you prefer, x plus 2y, putting it in the usual order. It's not going to be a linear system, however, where that kind of ordering would be important to get the matrix right. When you take the derivative with respect to x, you're not going to get a linear function. The partial with respect to x is going to be 3x squared minus 1, and then plus y. But with the Hamiltonian system, you have a negative sign in front of that, so now distribute the minus sign through, get negative, let's write it like this, negative y plus 1 minus 3x squared. I don't know, maybe that's not the most natural way to write it. Negative 3x squared minus y plus 1 would be fine too. Okay, that's the corresponding Hamiltonian system. What's the corresponding gradient system? Well, some of you know about gradient vectors. You've had multivariable calculus, which I think is most of you. Not necessarily all. You know that given any function that's differentiable, you can find its, like this, that's differentiable, you can find its gradient vector. It's a vector whose components are the partial derivatives with respect to the variables in the order they occur in the input. Typically written like this, the gradient of g, already using parentheses rather than the pointy brackets that I do in multi. Here's the gradient vector, written as a row vector. You can use these same partial derivatives. Y minus 1 plus 3x squared is the partial with respect to x. Partial with respect to y is x plus 2y. Using that same ordering, we can write down a corresponding system. dx dt equals y minus 1 plus 3x squared. dy dt equals x plus 2y. The right-hand side of the first equation is the partial of the gradient, or of the capital G in this case, with respect to the first variable. That's dg dx. And the partial on the right-hand side of the second equation is the dy, the derivative with respect to the second variable. Hamiltonian systems have solutions that lie on top of the level curves of the given function, the given Hamiltonian function. Have an idea? Any guesses about what happens to solutions for gradient systems? If they're still related to the level curves, let's go back over here and draw the level curves of capital G. There they are. So the Hamiltonian system solutions are going to be on top of these curves with certain directions. You got to get the directions right. You got to draw arrows based on the signs of dx dt and dy dt. Drawing nullclines is helpful too. Don't forget about that. Hamiltonian is going to be right on top. What do you think for the gradient? In fact, think of it this way. Think of it in vector form. Effectively, this system of two scalar equations is equivalent to a vector equation, d capital Y dt equals the gradient of g, evaluated at y. Think about it that way. Does that help you figure out what's probably going to happen? Think about what gradient vectors look like. If you've got multi, which again I think is most of you. If not all of them. There are always, what do you know about gradient vectors? Like say at that point right there. They're orthogonal, perpendicular, normal, there's 3 words for it, to the level curve at any given point, like that point right there. A gradient vector is going to be perpendicular to that curve at that point. And point in the direction from dark to light where the function increases. It points in the direction of fastest increase, instantaneously speaking, at the given point, which goes from the darker to the lighter and is perpendicular to the point, to the curve at that point. So solution curves have velocity vectors that are the gradient vectors. That's what this vector equation says. I emphasized that way back in chapter 2 in general. When you're writing a system of differential equations in vector form, that's like the velocity vector for your solution curves. Not necessarily a velocity for a mass on a spring or for a pendulum. velocity for the solution curve in the phase plane is equal to the vector field at that any given point. And the vector field in this case is the gradient vector evaluated at the given point. So if you draw the gradient vectors, those vectors are velocity vectors for solution curves as the solution curves go around. So the solution curves have to cross these level curves in a perpendicular way. They have to be orthogonal. Let's go ahead and see what the vector plot looks like. Those are scaled down gradient vectors there. I also added in 2 equilibrium points by setting those right-hand sides equal to 0 and solving for x and y. It's not too hard for that example. It's definitely doable. There's 2 of them. These 2. You see that these vectors are orthogonal to the level curves of G. The solution curves, well, what would have to look like? If I started right there, it'd have to go down a little bit this way, evidently before perhaps heading up this way or something. If I started here, you got to head up that way. I mean, some of these vectors are so small you can't tell what directions they're pointing in. Let's get the direction field in there. Those vectors are scaled down. They're not as long as they should be, but remember, when they're as long as they should be, the picture is too messy. If I use the vector scale option to make a direction field rather than the vector field, so that they're all the same length, then we see the directions better. So looking at this, it looks like that point's probably a source. The vectors are pointing away from it. Looks like this point's probably a saddle point. Going towards it there, some sort of stable separatrix, about like that. If you look at the arrows, and some sort of unstable separatrix about like that. Solution curves going like this in between the separatrices. StreamPlot will show that more vividly. And I got rid of the vectors in the vector field. I added nullclines. Don't forget about nullclines. And by the way, it is hard to draw level curves by hand, but you should certainly be able to take a system like this, I guess is the one we're talking about, and draw nullclines to help you draw it by hand, even if you didn't have the vector field or the level curves in the background. It wouldn't be perfect by any means, but you could draw a reasonable picture for it. Don't forget about nullclines. The x nullcline is where that's 0. Set that equal to 0. Solve for y as a function of x. You get y equals 1 minus 3x squared, an upside down parabola with a y-intercept of 1. That's what you see over here. Come back to the screen. A little hard to see maybe with the camera. This magenta colored curve right here. That's the x nullcline. Solutions are crossing it vertically. See? Up here, they're going upward. Along here, they're going downward. Along here, they're going downward. It's an x nullcline. This cyan colored line, which shows nicely, I think, hopefully in the camera, is where x plus 2y equals 0. In other words, y is negative 1/2 x when you set it equal to 0. Line with slope of negative 1/2 through the origin. That's this brighter cyan colored line. That's the y nullcline. That's where solutions cross horizontally. Where magenta and cyan intersect, those are your 2 equilibrium points. Again, for emphasis, you should be able to get a reasonable picture for this by hand without technology, except for the contour map in the background. Probably that contour map would have to be given to you. That would be difficult to draw without technology. But based on the location of the equilibrium points, based on the nullclines, you should be able to get a reasonable looking picture like this. And to confirm that this is a source and this is a saddle, you can use the Hartman-Grobman theorem. You can linearize. You can find the Jacobian matrix. See if I have that code here. Looks like I don't. Let me go ahead and add that code in here to confirm the nature of those equilibrium points. Here's kind of a nice flexible way to do it. I showed this to you before, although I don't think I typed it in. Call it J of x0, y0. X0, y0 being notation for an arbitrary equilibrium point. Hit the matrix button. Type capital D of f of xy comma x, capital D of f of xy comma y, capital D of g of xy comma x, capital D of g of xy comma y. That differentiates those functions, and then you can do what's called a replace all slash dot, and then inside the list go x arrow x0, y arrow, y0. So effectively what this does is it does the derivatives first, treating the x and y as variables, then plugs in x0 and y0 at the end. So you evaluate the derivative at those points. Oh, I don't think I called my functions f and g here, did I? I called them f grad and g grad. Okay, well I can call them f and g as well. Now I can use the Jacobian. Here it is again. What are the equilibrium points? Looks like they're these points, -1/2, 1/4, and 2/3, -1/3. What are the eigenvalues? Of J, the Jacobian, evaluated at -1/2, 1/4. We thought that point was a saddle point, so we should get 1 positive, 1 negative. Yep. And we thought the other one was a source. It didn't look like it was spiraling to me, and in fact, it can't spiral for gradient systems. It can't spiral. It's got to be a real source. 2/3, -1/3. Looking right here to see that, those are the coordinates. Should be both real and positive. Yes. Okay? These are hyperbolic equilibrium points. The Hartman-Grobman theorem applies. The local linearization does confirm the one on the upper left is a saddle point and the one on the lower right is a source. What would the corresponding Hamiltonian system look like? Well, it would have the exact same equilibrium points and the exact same nullclines, though the role of the nullclines would get switched. For the corresponding Hamiltonian system, the magenta colored thing here would no longer be the x nullcline, it would be the y nullcline. Look at the level curves, they cross it horizontally. And the solutions for the Hamiltonian would be on top of the level curves. And the cyan along this line would switch from being a y nullcline to being an x nullcline. Look at the level curves that are crossing it vertically with vertical tangents. What directions do the solutions go? That's important too. You have to look at the sign of dx dt and dy dt. Let's focus on the sign of dx dt here. dx dt is x plus 2y for the Hamiltonian system. That'll be positive when x plus 2y is positive. X plus 2y being positive, that's equivalent to 2y being greater than negative x, which is equivalent to y being greater than negative 1/2 x. Right? Not making a mistake there. No multiplication by negative numbers, so the inequality stays the same direction. So if we're above the cyan line, above the line with slope of negative 1/2, that's when dx dt is positive. So Up here, solutions are moving to the right, generally speaking. Up or down, but to the right. The xdp is positive. So you draw arrows moving along in this direction, from left to right, up here, for the Hamiltonian system. And down here, below the cyan line, they'd be going right to left. The xdp would be negative. And we can confirm that with StreamPlot. Here's the ultimate picture where I combine these two pictures. Yikes. Woo. Look at that spaghetti. Can you see everything? So same nullclines, same equilibrium points, though again, the nullclines switch their roles. The blue solution curves are for the gradient system, and the green ones are for the Hamiltonian. You can see the directions. The Hamiltonian one would be perhaps harder to draw by hand because effectively you'd be drawing the contour map. But again, you should be able to get a basic graph because you can get the equilibrium points right, and you can draw the nullclines.
What does Hartman-Grobman say?
Hartman-Grobman is about linearization. It's about saying what kind of equilibrium points do you have. And again, for the gradient system, that's a source, that's a saddle. You never get any spiraling with gradient systems. You never get any centers either, actually, with gradient systems. However, with the Hamiltonian system, look at the green ones, that's a center. This is still a saddle point. You're never going to get any spiraling with Hamiltonian systems, but you could get centers. Technically speaking, the Hartman-Grobman theorem doesn't prove that because the Hartman-Grobman theorem only applies to hyperbolic equilibrium points, and for the Hamiltonian system, the center, it's not hyperbolic, it's linearization, has purely imaginary eigenvalues. However, because it's Hamiltonian, it's effectively the Hartman-Grobman theorem combined with the fact that it's Hamiltonian says that even though that's not hyperbolic, it's still going to be a center.
Okay.
We're not proving any of this stuff, by the way. All those theorems are too advanced to prove in this class. We're trusting them. They should make some intuitive sense. Work on trying to draw these things to the best of your ability by hand. I suppose we're to the point, however, where we don't really have problems that are going to be on assignments where you're going to have to do that. In prepping for the final exam, there will be one problem where I'm not going to give you the vector field in the background, or the StreamPlot, or I might give you the level curves for a Hamiltonian problem, I might not, and maybe you try to get just the basic picture right, and don't worry about getting it exactly right. I mean, nobody can do all these things perfectly by hand anyway. Even with a computer, it's just approximations. So it's perfect as far as our eyes can see, but things still are being approximated. Is this related to some other stuff, like Lyapunov functions and trapping regions? Yes, it is. With gradient systems, given a function g, creating a gradient system, which I guess is this one, not that one, this one, the function negative g, or negative g of xy if you prefer, is a Lyapunov function for a gradient system. Which should make intuitive sense, if you think about it. Come back to the picture here. Let's see the time here. Okay. Come back to the picture. Focus on the blue ones. Ignore the green. You okay with that? Is the camera okay with that? Can you tell the distinction between the colors?
Yeah.
The blue ones, the gradient ones, going away from this equilibrium point, that's a source. You're traveling perpendicular to the level curves from low values to high values, from dark to light. In other words, capital G is increasing along solution curves. Lyapunov functions decrease along solution curves, so it should make sense if you just change the sign, put a negative sign out in front of capital G, that should be a Lyapunov function. You can confirm that with a derivative calculation, once again using the chain rule. Calculate the derivative with respect to time of negative G along the solution curve. Again, it's important that I emphasize that's a solution curve. I don't have formulas for those functions, but that's okay. I don't have to simplify the formula for the function that I'm differentiating here. I can just use the chain rule for multivariable calculus in this form. And then use the fact that since I'm assuming that's a solution curve, that the dx dt can be replaced by this, which I'm just going to write as that, and dy dt can be replaced by this, which I'm just going to write as that symbolically. dg dx times dg dx. That's not a second partial, that's a first partial squared. Right? dx dt is the partial of g with respect to x. By the form. Plus the partial of g with respect to y times the partial of g with respect to y. There's t's in the background that I'm not writing. The point is this is true for all t. Even though you don't see a t explicitly in there. And that's, oops, forgot my negative signs, didn't I? I was differentiating the negative gradient. Should be negative sign there and a negative sign there. Giving you a minus sign there and a minus sign there. That's less than or equal to 0 for all t as well. Is it only equal to 0 at a discrete set of t's? That's not something we've proved here, but it would be true. In fact, I can't think of a reason why it would ever be equal to 0 except at an equilibrium point. It's crossing these level curves orthogonally. Except at equilibrium points, that's going to be a strict less than 0. That is a condition about Lyapunov functions, by the way. You do think about this derivative at non-equilibrium points. That's something I forgot to mention. Because technically speaking, it would equal 0 for all t at an equilibrium solution. So technically speaking, I should say this is a non-equilibrium solution curve. How about trapping regions? Well, you would have them in a sense by considering sets of points where the Lyapunov function is less than or equal to some constant. Those sets are trapping regions in the sense that once solution curves go inside them, they stay inside them. That's a little tricky here again because I need to think about with the Lyapunov function being the opposite of the gradient of the capital G, that if I was graphing negative g, if I was graphing the Lyapunov function, it would be dark up here and light in here. The shading would get switched. The set of points where the Lyapunov function is less or equal to some constant then, in this picture for this gradient system, would include, for example, if I made the constant be whatever the value of the capital G is along this curve here, 1.24. Let me get it to stay. That level curve is where capital G equals 1.24. And all the points where it's less than or equal to that, points up here, I'm talking about for negative G, not G itself, would consist of points where solution curves go in and they don't go out. It would be a set about like this. Now, ordinarily we don't consider infinite extent trapping regions. Ordinarily we consider finite extent trapping regions. Bounded is what they're called. So in reality, if I was going to think about this with in the context of trapping regions, I'd really want to switch my system to not being a gradient system, but to being the opposite of a gradient system, which is actually still a gradient system, but just for this function instead of the original function. So should I say that again? What I'm going to do is I'm going to consider the gradient system corresponding to that function, negative g, rather than g itself. So in this code, I'm going to switch the StreamPlot here for the gradient system to having negative signs in front of f grad and g grad. So the solution curves, the blue ones, are going to go in the opposite direction now. And this one has become a sink now instead of a source. That's still a saddle. Solutions are going in the opposite direction. It's the wrong ContourPlot, though. ContourPlot. Oh, I made that with this thing, contour now. Okay. Bear with me here. Let me do a little more copying and pasting. Let me change this g to a negative g. Now we'll get the shading right too. So the contour map you're seeing here is for negative g. Same level curves, but shading is different. Dark here, light here. Dark down there, lighter over here. Now you can see trapping regions in a way that's more typical. For example, focus on the sink. Any one of these ovals would represent the boundary of the trapping region for the system. Take this one here. And ignore the green, by the way, when I'm circling this. Focus on the level curve itself. By the way, the green is not exactly on that level curve, it's on a different level curve. So you can see the difference between them. Focus on this level curve for this function. The set of points for which this function with this contour plot equals whatever the values along this level curve, or higher actually, which will include points inside the boundary, would be a trapping region for this. You can see the vector field, the solution curves are going into that region. The vector field would be pointing at an angle bigger than 90 degrees from an outward pointing normal vector all the time, all along this boundary. That's going to be a trapping region. Once solutions get inside, they can't go outside. They're trapped. That's the idea. The theorem one of the theorems I tried to emphasize related to that was a proposition here that if you've got a trapping region, say for a two-dimensional autonomous system, then there's at least one solution that stays inside the trapping region for all time, not just as time goes forward. In the picture that I just showed you, the solution curve that stayed inside that trapping region for all time was the equilibrium point. Okay? You could have more than just an equilibrium point staying inside the trapping region for more time, though. You could have a periodic solution. You could have solutions in between a periodic solution and the equilibrium point stay in the middle of the periodic solution. That kind of thing can happen. You can have other equilibrium points. It can be more than just one equilibrium point. This proposition, this fact here is still true. There's a solution, at least one solution curve that stays inside there for all time, not just as time goes forward. We also have this thing called the Poincare-Bendixson theorem, which can be stated in lots of different ways. The simplest way to state it is, I think, is as I have here. Suppose you've got a planar vector field mean in the plane, system of two equations, two scalar equations. And suppose R is a trapping region, and any of the senses above me is referring to the extra reading. I defined what I call a smooth transversal trapping region, where the boundary is a smooth curve, or maybe a union of smooth curves, some inside the given smooth curve. a piecewise smooth transversal trapping region. The word transversal basically just means the vector field is pointing directly into the trapping region, not tangent to it. There are more general kinds of trapping regions that can include situations where the vector field is tangent to the boundary of the trapping region at certain points, and it's still a trapping region. Don't worry about that. Just imagine ones where the vector field is pointing directly into the region along the boundary. If the system has no equilibrium points inside the trapping region, then there must be a periodic solution, okay, inside the trapping region. I did mention, and I'll mention again now, that you're not going to apply this really to trapping regions that just consist of one boundary curve, because such trapping regions actually can be proved to have equilibrium points inside of them. So you're typically going to apply this Poincare-Bendixson theorem to trapping regions that are annular in nature, ring-like. So there's a region. If you happen to know the vector field always points inward along the boundary, meaning the dot product of such inward pointing vectors with outward pointing normal vectors is bigger than 90 degrees all the time. Maybe you get something like this. And along the inner boundary as well. Something like this. The Poincare-Bendixson theorem says if you don't have any equilibrium points inside that ring, there's got to be a periodic solution inside there. Could be more than one, but there's got to be at least one. There's got to be at least one solution curve that's a closed solution curve. It's a periodic solution like that. Let's talk about a few minutes briefly applying this to something called the van der Waals oscillator. I'm going to briefly talk about this today. I'll talk about it more on Friday.
Can I ask a quick question?
Mm-hmm.
So it has to be a ring, you're saying? You can't have just a circle?
We can't really apply the Poincare-Bendixson theorems to disks or ovals because there will be, by some other theorems, an equilibrium point inside there. The way I've stated it, suppose there's no equilibrium point inside the trapping region. If there's no equilibrium point inside the trapping region, then there's got to be a periodic solution. It's just based on the way I've stated it. There are other ways to state it, but don't focus on proving the existence of a periodic solution so much. This system here, with right-hand side functions, both of those things, is called the van der Waals oscillator. Don't worry about the equations for the moment. I just want to show you something here. It turns out that for certain values of a parameter, the phase plane for the van der Waals system looks like this. See it in the picture here. Notice the green annular region that I've drawn the boundaries for. If you look at this carefully and think about it, it's got to be a trapping region. However, if you try to construct something simpler looking, just notice how the vectors, the StreamPlot vectors are going into the region as time goes forward. They're pointing into the region. Based on the way it's slanted, if I didn't slant it in this way, for example, if I tried to make a trapping region where this line continued down here before going up, instead of having this slanted version here, turns out that it would not be a trapping region anymore because along here the vector field is actually going to point out. So the main moral of the story here is trapping regions can be difficult to construct, okay? Without trying to explain the details of how I created the slanted sides here to make it work. Notice that they do make this a trapping region, but you might imagine in looking at this that this would be hard to figure out what the trapping region would look like. Therefore, because of the Poincare-Bendixson theorem, there is a periodic solution in there. It's the black curve here. The red curve is a x nullcline, it looks like, and the orangish curve, the y-axis, is a y nullcline. I'll let you think about that. I'll talk about it more on Friday. For the remaining time, I want to introduce the idea of a Laplace transform. Chapter 6. I'll definitely give more time to this trapping region stuff and the Poincare-Bendixson theorem on Friday. But I think it would be good to introduce you to Laplace transforms. Even if it means today doing kind of a shoddy job with that. By the way, the homework due Friday is the last homework to turn in. Completion assignment. There will be no homeworks to turn in next week. You'll be working on the project, but you'll also be studying for the final exam, which will include some suggested problems to work on with keys. Mostly about Chapter 6. You'll have some Chapter 6 problems here due Friday with completion assignment. But after that point, the Chapter 6 problems would be things to do on your own as much as you want to help you study for the final exam. The Laplace transform of a function, called the function f of t, is another function. There's really three functions going on in this notation. F of t is going to be an ordinary kind of function that I'm going to plug in there, maybe t squared, maybe e to the t, things like that. What's that thing? That's an L, fancy L. Cursive L, very pretty, right? Fancy L, that's the Laplace transform. The Laplace transform is a function that takes an ordinary kind of function as input. And the whole thing, the whole expression, is another function. It gives you, the Laplace transform gives you a function as output. Very strange. Actually, it's not so strange if you think about it carefully. The derivative operator is a similar kind of thing. You got a function there. d dt takes that function and gives you another function. There's really three functions in this notation here. F of t, d dt, and the whole expression representing the derivative. d dt and L are different kinds of functions than you're used to, though. Their inputs are not numbers and their outputs are not numbers. Their inputs and outputs are functions. And when that happens, we often call them transforms. And that's why it's called the Laplace transform. Laplace was a contemporary of, I think, Euler in the 1700s, named after Laplace. What does it equal? How do you find it? It's an example of something called an integral transform. You have to find the answer by doing an integral. In this case, it's an improper integral to boot. Actually, most of these transforms are improper integrals. This is analogous to something called the Fourier transform, which you may have heard of before. This is easier than the Fourier transform, though. You integrate the given function, little f of t, times e to the negative st dt. I claim that this is a function. And you scratch your head and look at it and you say, well, you're doing an integral, won't you get a number? You get a number for each individual value of s. But as s varies, you get a function. This is a function of s. Do a quick example. What is the Laplace transform of e to the negative 5t? So the function I'm plugging into the Laplace transform is e to the negative 5t. The Laplace transform itself is a function. It operates on the input to give you an output. That output is going to be a function of a new variable called s. That can be found by doing this integral. This improper integral. Use properties of exponents. You can write this as a 1 exponential integrand, e to the negative s plus 5 in parentheses times t, dt. Technically speaking, such improper integrals are limits. I will be more like a mathematician today and write a limit sign. If I was a physicist, I probably wouldn't bother with the limit sign. But just to remind you, there is a limiting process involved, assuming the limit exists. Maybe for some values of s, the limit won't exist. Maybe for some values of s, this improper integral won't converge. And other values of s, it will converge. In fact, that is what happens. Do the integral. You're going to get negative 1 over s plus 5 e to the negative s plus 5 evaluated from 0 to b. T goes from 0 to b. I should emphasize that. T goes from 0 to b, and I forgot my t in here. Limit as b goes to infinity. Negative 1 over s plus 5. Just leave that outside the parentheses here. Plug in t for b, get e to the negative s plus 5 times b. Plug in b for t. And then subtract what you get when you plug in 0 for t. E to the 0, which is 1. Does this limit exist as b goes to infinity? It depends on what s is. S can't be negative 5. We don't want to divide by 0 here. It can't be negative 5. Like this whole calculation is not valid when s is negative 5. Starting right there. In fact, you want this coefficient of the b to be negative, the entire thing here, which is going to happen exactly when s plus 5 itself is positive. This converges if and only if, IFF, if and only if s plus 5 is greater than 0, which is equivalent to s being greater than negative 5, and diverges otherwise. In the case where s is greater than negative 5, what is the limit? This thing, okay, here I'll be more like a physicist, this thing goes to 0 as b goes to infinity. That's not the best notation to use in reality, but I'm running out of board space here. So you have the limit as b goes to infinity of this, that's 0, this is a constant, it stays the same, this is a constant with respect to b as well. You really have negative this times negative 1. The negative signs cancel, you're left with 1 over s plus 5. Then you sit there and say, that's interesting, so what? So what? What is this for? Why is it in differential equations? It helps you solve differential equations. I'm about out of time to do so. In section, let me just say what to expect in your reading and in your completion assignment. In section 6.1, they use it to solve first-order non-autonomous equations of the form, typically dy dt plus a times y equals some function of t, which in the first section will be an exponential function of t, in fact. Some constant b times e to the ct, say. They focus on using the Laplace transform to help you solve that. Now, what you're going to find when you do the reading and try the problems is the Laplace transform method for solving this is harder than the chapter 1 methods. Much more work. We already know how to solve this kind of equation with 2 different techniques from chapter 1. Integrating factors and method of undetermined coefficients, guessing, educated guessing. You will see the Laplace transform is harder and much more work. However, So that begs another question. Why do it? When we get to the next section, it becomes more valuable because we introduce right-hand side forcing functions that are not ordinary kinds of functions. In fact, they are discontinuous. We're going to talk about something called the unit step or Heaviside function is another name for it. Discontinuous forcing functions. The old techniques don't really work. The new technique with the Laplace transform works. And in our final section that we do for this course, 6.3, we go on to second order equations, forced harmonic oscillators really, where once again the forcing function is discontinuous. So the Laplace transform is going to give us a lot of value out of those kinds of equations. We're not going to be able to solve it any other way. Well, that might be a bit of a stretch, but other ways will be more complicated. The Laplace transform will be better. Not easy, but better. All right, have a good day. See you Friday.